Okay, this is the example from electrical engineering. A 12-volt battery is connected to a series circuit in which the inductance is 1 Henry and 1 Henry and the resistance is 10 ohm. So determine the current I if the initial current is 0. So the inductance is I will make a correction. It is 1/2 Henry. Okay. So this is a RL. This type of circuit is called as the RL circuit. RL circuit, where R is for resistance and L is for inductance. So inductance is like this, represented like this, and the resistance is represented like this. Okay, and then they are being connected by a battery. So with a voltage drop. So total voltage drop across inductance and the total voltage drop across the resistance is equal to the voltage of the battery, E. So here in this case, L is equal to half Henry and R is equal to 10 ohm. So in both the inductance and resistance are related with the current I, okay, and which changes with time. So there is in electrical engineering there is a law which is called as the Kirchhoff's law, which says that in a series current, in a series circuit, the total voltage drop is equal to the voltage drop across inductance and the voltage drop across the resistance. And in fact, there can be another type of element which is called as the capacitance. So if there is a capacitance, then that will be C will be also added. But in this case, it is only a RL circuit. So accordingly, there can be RC circuit, resistance capacitance circuits, or there can be RLC circuit, or any other combination. Okay, but we will be only talking about the RL and RL circuit in this case. So for this RL circuit, so total voltage drop is 12 volt, which is given over here. So this 12 volt will be equal to the voltage drop across this. So the voltage drop across inductance and plus resistance. So voltage drop across inductance is represented by VL, and its formula is the value of the inductance multiplied by the change in current, okay, di over dt, rate of change of current, and the voltage drop across the resistor is simply the resistor times the current at that time, okay, So here is the change in rate of change of current, and here is the current. So 12 is equal to VL plus VR. So VL is L di over dt plus VR is RI, and that is 12. Or if I input the values of L and R, so it will be 0.5 di over dt plus R is 10, and then it is 12. So it is an R then I. So now this is a first order linear differential equation. So we can make it in a standard form. Di over dt is equal to 20, plus 20 divided by 0.5. So it will be 20. I is equal to 24. So if we solve this differential equation by the integrating factor, so integrating factor will be E integral 20 dt. Okay, so it will be e power 20 t, so it will be e power 20 t. So e power 20 t times I prime is equal to 24 e power 20 t. So again integrated, e power 20 t times I will be equal to 24 divided by 20 e power 20 t plus a constant, and I will be equal to, so we can simplify it. So from here we can simplify it. So 24 divided by 20 is 1.2, and then divided by e power 20t, so it will be just 1.2, and then it will be c e power minus 20t. So when it has been given that at time initially there was no current, okay, so in this from here then we can find that if we apply these two conditions, so I is equal to 0, 0 plus 0 is equal to 1.2 plus c into e power, that will become 20 into 0 is 0, e power 0 is 1, so value of c will be equal to minus 1.2. So therefore the equation for the current will be value of c will be minus 1.2. So 1.2 we can take common, so it will be 1 minus e power minus 20. So as if in this equation we can see that at a very infinite time this term will be almost 0, so the current will be 1.2, the value will be 1.2.